some of the things that we would like to do with digital twins in the future. It certainly ties into the Internet of Things and so forth. I'm not going to talk a lot about fluid mechanics. Most of the examples I will show would be for linear, nonlinear structures. But the connection, some of the extension can be done. Okay, so what is it that we are trying to achieve here? Well, some of the things that we would like to do going forward is to think about ways in which we can maintain, let's say, large-scale scientific equipment. What you see is the Chinese telescope. It's the largest telescope in the world. It's very sensitive. It sits outside, so maintaining and operating that in an optimal way as the asset ages is sort of one of the ideas of digital twins. It obviously also lends itself to bridges, critical infrastructure of any kind, systems of satellites, for instance, and there's some people who have their microphones on. Maybe it would be good to have. But anyway, and a very interesting one, which is also a very challenging one, is to build digital twins of aircrafts. They're obviously extremely expensive. Operating them, maintaining them is of critical importance. And how to actually do that is an open question at this point. So what is it that is common among these problems? What's going on? Okay. What is common about these problems is that with these problems they're complex, they're multi-physics, they're multi-scale, and we cannot hope to model them directly. And even if you could model them directly, sort of ab initio, then there will be a large amount of uncertainty associated with the problem, and it would be very difficult, if at all possible, to do directly. At the same time, we are going to need tools that allows us to make decisions, how to maintain, how to operate, how to optimize these machines. And machine learning could be an idea of trying to do some of these things, but there are a number of challenges when you think about it as a machine learning exercise, which is, let's say you take a bridge. You want to understand whether to do maintenance on the bridge or not. You're going to have some data of the bridge, but you're not going to have a lot. It's going to be sparse either in space or time. There's going to be noise. Some of the sensors will fail. And for some assets, airplanes, for instance, or satellites, it may be very expensive or perhaps even impossible to get the data. So some years ago, I don't know if maybe it's even 10 years ago, there was this famous article in Wired that predicted it was now the end of science. There's no reason to do science anymore. Everything was a data problem. If you have enough data, the data is the model, you go ahead. The problem is that the kinds of questions that I'm interested in here is not a big data problem. You don't have massive amounts of data you can swim in. You only have a little bit of data. And this separates things rather dramatically. And one of the questions you can ask yourself is, well, can you use the tools from artificial intelligence, neural networks, and so on, that only work where they have an incredible amount of data available, to situations where you have very little data available? And the short answer is, if you try to train a neural net with a little bit of data, it is a meaningless exercise. You will not get anything reasonable out of it. So the question is how to do that. And so this is what I call the small data problem. And this is the situation.
Oh, sorry, Jan. Sorry to interrupt. I accidentally, yeah, it should work now.
You accidentally muted me.
Yeah, sorry.
It's fine. It's fine. So the situation we live in for the kinds of digital twins that I proposed or suggested is not a big data problem. It's a small data problem. And if we want to understand that and look at problems that are very, very complicated, then this will not change. We will never have enough sensor data to accurately predict the behavior of an oil rig or an aircraft. So the only way that we can begin to understand these problems under also uncertainty is to begin to use modeling in combination. Now, if we can do it, it clearly will have a huge impact because we would allow us to optimize a number of things in operation and building, maintenance, and so on. The reality is that for many types of very expensive assets, bridges, oil rigs, aircrafts, you either run the asset until it fails, which is usually not a good idea, or you are overly conservative in maintaining it, which is expensive because there are no tools. So this is sort of the space that we're trying to live in, okay? And only by fusing the modeling with the data and our understanding of the problem can we begin to look at these types of problems. But in order to enable this path of combining what we know about modeling and 500 years of science with how we actually solve these problems, and then we actually use the data in order to build models that are truly digital twins, is the challenge, and it's a big challenge. It's a very, very rich problem. So that statement, so what is a digital twin? Well, a digital twin is a computational model that has true predictive value. It is fast enough to explore variations, so you can understand decay, you can understand uncertainty and the impact of it. But at the same time, it's accurate enough to have predictive value. And once you have a model like that for a real asset, so here's an example. There's a company here in Lausanne that works on digital twins for large assets. Here it's a ship. Once you have that, if you can exercise this model fast enough, you can begin to make decisions based on it. So that's the idea of a digital twin. It's an old idea. It's been around certainly since the 70s. But if you talk to all the big companies, the Siemens, the General Electrics, even Airbus, they all would like a digital twin, but the problem is so complicated that they don't know how to do it. They can do pieces of it, but putting the whole pipeline together is challenging. So what is it that you need to do? Well, you need to be able to build models. You need to understand how to place sensors and integrate the data using the technology that you have. Now, once you have a model that is true to the data, you can use the model to generate data. And once you generate data, and lots of it, you can begin to use artificial intelligence to do decision support. But because it's ultimately a small data problem, you have to go to the modeling phase. Otherwise, the AI tools simply will not have any chance of being successful. So in order to do all of this, there's significant advances needing, and we have done them in computational math, in modeling, and sensor technology, and so on. And this vision is sort of within reach. And what I will show you today is rather than giving one talk in depth about a particular topic, I'll show you several elements of some of these issues, some of these developments that sort of point in the direction that we could hope to be able to do something like this in a not too distant future. So why would we do it? Well, I've already hinted at it. There was a nice figure down here in a review paper about a year ago, where the enabling technologies, that's what we all do, the computational modeling, physics-based modeling, data-driven modeling, all of this is sort of, but that's an enabling technology. And if we can do it, then we can begin to build digital twins that can have value for risk assessment, predictive maintenance, scheduling, monitoring. There's a number of different activities that we would like to do for very complex systems. Okay, so the key is here, we're trying to do this for complex systems. And I'll show you some examples later on. There was a report that came out from Siemens just a few months ago, all about digital twins. They have been talking about digital twins probably for 2 decades, and it's still not something that they're able to do on a big scale. So here's the list of things I'd like to discuss. I don't know that I will make it through all of them, but I will at least touch on some of them. But I'll start out by making the argument that before we even start this discussion, we're going to have to focus on the ability to build models of complex infrastructure structures I will focus on, but it could also be fluids that are so fast that we can allow ourselves to sample the model many, many times. Because only then can we begin to understand the dynamics of the problem, we can generate the data sets, and we can start using ideas of machine learning to make decisions. So, and then I will go into some examples. We'll see how far we make it. So, okay, reduced order modeling. So what's the idea of reduced order model? Well, what's the idea of a digital twin? We like to develop digital twins that are data informed. So in order to do that, we're going to have to have the ability to build the twin and sample it so that we can understand its behavior. It could be for uncertainty quantification. I'll show you an example for sensor placement, a number of different things, situations where we need to be able to solve the problem quickly. If every simulation is days of supercomputing time, then this becomes impossible. So we're going to have to build models that are as accurate as we need, but they must still be fast. And then we can begin to fuse that with whatever data we have available in order to understand uncertainty quantification and so forth. Okay, so the reduced order modeling, in however you choose to do it, is a key enabler if you want to build digital twins. If you don't have fast, accurate models, you cannot do many of the things that we need to do, and you cannot generate data sets that can be used in the context of artificial intelligence. So what is reduced order modeling all about? So I'll just do a couple of slides so that you know the context. I will use it in all the examples later on. So let's say you want to solve a PDE, doesn't matter which one it is. X is space, mu is parameters. The parameters can be boundary conditions, material coefficients. It can also be geometry. It can also be time. And you want to solve this problem for many values of the parameter mu. Now, of course, you can use your favorite solver, finite difference, finite element, whatever you wish. If you want to do this accurately, then the number of degrees of freedom, n, is going to be very high, and therefore it's going to be slow, and you have to solve it every time you solve for a new parameter mu. So what we're looking for is an accurate way of trying to evaluate the solution at reduced complexity. Now, let us assume, and this is an assumption that one can then check, but let us assume that somehow there is another coordinate system. Instead of U, it's called Q. Q has many fewer degrees of freedom, and they're related through this matrix V, which is tall and skinny. So it has n number of rows in H, which is the number of degrees of freedom in the big problem, and NR is the number of degrees of freedom in the reduced model. If NR is much smaller than in H, then you have a reduced model. One way of thinking of it is I'm going to take a basis instead of my finite element basis. I'm going to choose a basis which is problem specific. If I can do that, if I'm willing to restrict myself like that, then in fact I can do a much better job within a certain class of problems. Now, you do a Galerkin projection, and we get now a problem, in this particular case, which is instead of being NH by NH, it is now NR by NR. It's a dense problem, but it's very, very small. So instead of 10,000 by 10,000, it is now 10 by 10, which means you can now solve for every new parameter extremely fast. This is the idea of a reduced order model, basically finding a problem-specific basis. Now, does this always work? Well, basically what you're assuming is that as you vary the parameter mu, the solution changes, but it changes in a smooth way. so that you can capture, you can approximate the solution manifold. So this is what M. So as you change mu, the solution moves around. But you're basically making an assumption saying that at least in a certain region of the parameter mu, I can approximate this manifold very accurately with a linear space. Sometimes this is not, in fact, correct. But if it is, you can do a good job, you have a good model, and you can achieve this. Okay, you can test whether this is accurate and so on. There are ways of dealing with that. Now, how would you test that? Well, if I have a problem, in this case, it's electromagnetics. It's a wave that hits the cavity, the box there. Okay. There are two parameters. That's the wavelength, the wave number, 2 pi over lambda. That's called k. And then there's the angle of incidence. And we sample it 3,600 times. Okay, so you solve it 3,600 times. Then you do an SVD of these solutions. And you find that with only 200 solutions, you should be able to solve the problem with an accuracy of 10 to the minus 7. So you don't need the 3,600, but you only need the 200. And in fact, if you're interested in a 1% error, you can probably do it with 100, or actually maybe even 50. Okay. Now it doesn't get you any information about which 50 that is, but it tells you that in fact there is a low-dimensional representation of the solution manifold, and you can try and go ahead and see if you can find that. So this is how you would test it. You can also do it in a more theoretical way, but it gives you a sense of how it works. Now, when does it work? Well, actually, there is an elaborate theory that allows you to certify these models so that you have a reduced order model that you can guarantee is as accurate as you need it to be compared to UH, which is the high resolution accurate solution. Okay, so we're not going to spend time on this. It's just for you to know that there is an elaborate theory these days on how to do reduced order model for linear problems. Using this kind of technology, you have error estimates, everything is there. Okay, there's a book, you can download it for free. That's the only reason I bring it up there. That tells you and gives you an idea. You can do it for electromagnetics, acoustics, elasticity. You can do it for Navier-Stokes, quadratic nonlinearities, and so forth. So there's a huge body of work there that allows you to solve problems, complicated problems, at very low cost. So let's see how we can use that. So the first example is I like to detect failures in a structure. Let's see if I can. So the question is this: let's say I have a structure, a building, a bridge, whatever, and I'd like to know if it's failing or if it's about to fail. I don't know what type of failure it is. I cannot possibly characterize all possible failures for a bridge. So I cannot build a machine learning that can technology that can identify known types of failures, because it's an impossible exercise. At the same time, the bridge has natural variations. The materials vary, they change over time, they decay maybe a little bit. Doesn't need to be a problem, but it nevertheless happens. So in a structure like that, how can you detect failures, say, using sensors? Okay, so the idea that I will present is the following. So I'm going to build a model of the healthy structure, the one that I know. When it was built, whatever, to the best of my ability, I built a model of a healthy structure. Then I use that model to generate samples of sensor signals over natural variation. Say I allow the materials to vary, perhaps the geometries to vary, whatever. And every time I exercise my reduced order model, which I can do at low cost, I extract sensor signatures. And then I will use these sensor signatures with what is called a one class SVM. I'll show it in a minute. That basically can detect outliers. Okay, so let's see how it works in a little more detail. So these are the structures that I will show. It can be more complicated ones. So it's a linear elasticity problem. You have waves that propagate around. And the idea is I would like to put a source on the structure somewhere, as well as some sensors. And then by actively exciting the structure, I would want to know from the sensors whether something is wrong or not. I allow for uncertainty in the materials, and that the Young's module as well as the Poisson ratio nu can vary. But other than that, it's a linear problem. So here are sensors placed on the 3D structure as an example. The structure is excited with the green dot is. It's a broadband source. Think of it as a hammer that hits it. And then you have sources. Then you have sensors that records the signal. This is called active waveguiding. Because if you want to actually see failures far away from the source, you need to look at it as a wave problem. It cannot be a static problem. Then you can't see them. So how does it work? Well, again, I assume the materials has natural variations. You sample over all these. This gives you a large data set that you have now created. You identify features in the time traces at the sensors that are failure sensitive. So let's say the arrival time of the first peak, the maximum amplitude of the signal, and so forth. And then you use that to train a one-class SVM, which is a one-class SVM is you give it all the data and it tries to classify all of it as being healthy. So it creates a boundary for all the healthy data, and anything that is classified as outside of the boundary is called an outlier, and this can be scored depending on how far you're away. So you get an anomaly score, and then you can decide based on that. Now, in fact, what we do is we do it in a two-stage process, where first we look at the signal from all the sensors. Now, if all the sensors are good, then obviously nothing is wrong. If all the sensors if some of the sensors are lighting up as being something is going on, then we would say we need to do a second stage, and then we would look at the local sensor signals. So there are two SVMs. So there's one which does the global analysis, and then there's one that does it at each sensor at a time. And with the second stage, we can then localize the failure. So just to show you that it actually, at least empirically, works. So here's a two-dimensional structure. The beam is broken. You have three sensors: sensor 6, 8, and 12. They're placed at the end of the arrows, and you can see that at the curves below, the black line is the time signal that you get in the damaged structure, whereas the blue and the orange ones are signals that you get under variation in the healthy structure. You can see that there's a distinct difference, certainly in particular in sensor 8, which is not a surprise because there's the source is where the triangle is. So if that beam breaks, sensor 8 would be very much impacted, you would expect, and whereas sensor 6 and 12 would be impacted less, you would imagine. That's in fact is exactly what you see. Now, if you go through this exercise, so here's a number of broken beams or cracks, if you will. The source is the same, and the sensor signal here basically says if it's a round circle, nothing is going on, and if it's a red box, it means it's a major damage. It predicts a major damage in the neighborhood of the sensor. Whereas if it's a star, it predicts a minor damage in the neighborhood of the sensor. Now, this is not an exact science, but it gives you a sense of where the failure could be and whether it's a large failure or a small failure. You do the same thing in 3D. Again, you have small cracks, either broken beams or small cracks. And you can see that the ones that are red are the ones that light up, saying something is going on. You need to look at that part of the structure to see if there's something going on. So this is an example of a combination where you do careful modeling using reduced order models with uncertainty quantification on top of it to build the data set that you use then to drive an SVM classifier that you then use to detect failures or not. Now, this was for a linear problem. If you want to do nonlinear problems, it gets more complicated. So as we just went through, here's the reduced order modeling again. You get the small problem on the right-hand side, everything is fine. But if it's a nonlinear problem, then the problem is that A, your operator, depends on the solution. So therefore, you would have to evaluate it every time. And then you lose the benefit of the whole method. So what we're doing is, so you can play some games, there are various ways around that, but if A is a general operator, this becomes very complicated. So what I'm proposing here is actually to build a reduced order model using machine learning as a surrogate model. And then once you have the reduced order model, you can go and do the exercises that I just talked about using building data sets. So how does that work? Well, so this means now that we will again represent our solution U as a function of two. There's a spatial variation and there's parameter variation. The spatial variation is exactly as before. This is the eigenvectors or the V that I call V. And instead of solving a small problem in order to find these Qs, I will train a machine learning process. In this case, we will use Gaussian process regression. You can also use neural networks. We have done that. It also works. But the neural net is sort of the last stage. It's, if nothing else works, you can do the neural net. The Gaussian process, if it works, is much faster and much simpler. And then once you're done, you have created a surrogate for the coefficients, and you never solve the problem again. So in this case, we use Gaussian process. It's not so important what that is. Think of it as you're trying to represent a function with kernels, so it's a little bit like a reduced basis method. No, like a radial basis, radial basis function methods. Okay, so you don't have any grid or anything. It's completely randomized or unstructured where you have the points, and then in the Gaussian process, since you use the data to find the hyperparameters for the Gaussian process. And think of the width as the Gaussian over space in order to represent the solution. And the beauty of it is that not only do you get a solution, say as in the curve to the right, so the crosses are the training points. The line is the predictive mean, but then on top of that, you also get an estimate of how good of a job you're doing, which means you have immediately a measure of the accuracy of your prediction, or at least a sense of it. So this you can use, for instance, if you have the solution here, says I can do one more measurement. But it looks that as if I should do this around x equals 5, that would be the right place to do it because that's where I have the biggest variation. So this is called active learning. You can play things like that. So again, so now we'll do nonlinear structures, but it'll still be structures. If you're not familiar with it, it's not so important. But it's a nonlinear problem. And this one is a classic problem that people have looked at, and this is called the leaf frame. So, so there are two parameters, mu1, mu2. And the material is a nonlinear material. And then what happens is you apply a force, F, to it. And the frame on the left upper left, as you push this leaf frame, it distorts in very serious ways, and then ultimately flips back. So this is actually a surprisingly difficult problem to do, but with this technique you can do it. But the interesting thing is you look at the time. So once you have built the model here, on the left, you could see if you want to solve the problem for one parameter value, it takes about 23 seconds. Whereas once you have built the reduced order model to solve the same problem, it's 3 orders of magnitude faster. Okay, and this is what you need in order to build digital twins. Here's another example. This is a twisting column, so there's just, again, the material is nonlinear, and you start twisting it, and you can see how it spins up. It's a time-dependent spin up. And again, here in this case, in fact, once you have built the model, it is 8 orders of magnitude faster for the nonlinear problem. So once you can do that, you can start doing nonlinear large structural problems, and then you can do uncertainty quantification and so on. All these things are only possible if you can solve the problem fast enough. If every time you have to sample here, it takes basically 20 minutes to solve the problem for one parameter value, and you have 10,000 parameter values, there's just no hope. So it starts with the reduced model. You can also do fluid mechanics if you wish. So here, incompressible Navier-Stokes. It's exactly the same way. You build a model. Now you have time also as a parameter. And if you look at so the Reynolds number, of course, is relatively low, but you can see that you capture the shredding behind the cylinder very well, and at the orders of magnitude higher speed. Now, of course, you cannot take this model and say, oh, I changed my mind. I would like it to be a square instead of a round cylinder. Then you're going to have to start again. And this is how you gain the speed. Again, you have the uncertainty that comes, well, you have the natural measurement that comes from the Gaussian process, that if you predict a signal, a solution, again, here's for the Reynolds number, or for the fluid flow, the black is the correct solution, if you will. The red is what you get from the Gaussian process, but at the same time, you get an error bar, and you can see that it fits within the error bar very well. So there's an error circuit that you can use to understand how well you're doing. Sensor placement. So let's maybe that'll be the last example. So here's the question. In fact, there are 2 questions. I have a structure, I'd like to put sensors on it. I only have a finite number of sensors because they all take energy. So I have a certain number of sensors I can put on in order to do that, and I cannot afford more than that. So the question is, where should I put them? If I want to learn as much about the structure as I can, and I have 10 sensors, where should I put them? Or the other question, which is equally interesting, is let's imagine people have placed the sensors for me. 10 sensors have been placed. What can I actually hope to see? Okay, very often you talk to people who have put sensors, let's say, on an oil rig, and so the sensors are here, but would like to know exactly what happens at the bottom of the sea. Now, is this even realistic? Is that possible? So these are sort of complementary questions that are very, very much related. So we need to make a couple of things here. We have to decide what it is that we want to measure. Now, it makes sense to measure something that suggests that there's a failure or not. We have already discussed arrival times, maximum height of the waves. We actually have 18 features that we look at. And then at the same time, when we are placing sensors, we have to also accept that we're placing sensors in a scenario where there's uncertainty, there's natural uncertainty. So this is not going to be an exact science where these sensors should be placed, but rather taking into account the uncertainty. So again, we use, in this case, sparse Gaussian process, but it's a detail for now. Use a variance of Gaussian processes. And then basically it's an iterative process where first you place the Gaussian, you pick the locations, you find the hyperparameters, you ask yourself, what is the maximum variance over your domain? You move the sensors to where that happens, and then you iterate like that. And then you do that for many, many different samples of the parameters in order to get take into account the uncertainty. You only have to do it once for a structure, so it's not a big deal. Here's an example. It's a T-beam. It's clamped at the end. It's free at the left. And we want to know, as you impose a force on it, where should I put the sensors, knowing well that it's an uncertain material. So here's the result. So if you can only put 4 sensors, then these are the locations. And what you see is that the little blue dots is the result of the sensor placement varying while I take into account the uncertainty. And then for each of these clusters, you compute a mean. And this is the location. Okay, so this is 4 sensors, 9 sensors. It goes up to 36 sensors. And you can see that basically it takes into account the natural uncertainty by placing it in the mean of where the algorithm predicts. And what this shows you is the variance reduction. So if you only have 4 sensors, it tells you that right where the sensors are, the colors are red, the error is relatively small. Well, no. So the blue means you have high variance, and the red means you have low variance. So this means where it's blue, you have a hard time measuring it with 4 sensors. But as you add more and more sensors, if you add them carefully, you can see that eventually you're reducing globally the variance in your prediction, which means with those 36 sensors, I can measure anything that goes on in my structure to within a certain accuracy. That's the idea. Okay. Now, just to show you an example of a real structure, so this is called a jacket. So this is what sits underneath an oil rig. And there can be forces on it to the left. It is the forces from the ocean actually hitting the structure. The colors gives you a sense of the forces on the structure. To the right is wind forcing. It is clamped at the bottom, and in fact, at the bottom, they can be nonlinear, but that's not so important. And if you go to this exercise and you ask yourself, well, if I want to predict behavior for this jacket, where should I put the sensors? And the algorithm says here. And then the table on the right it's not so important, the details, but these are basically 4 different cases of failures. You know, you break a beam or you do something to the structure. What is the chance that you detect it? And you can see that cases 1 to 4 gets increasingly bad. So if a beam is broken, then all 10 sensors tells you there's something wrong. If it's just a minor thing, like in case 2, well, you still get 85 to 90% reliability over variations as long as you place the sensors correctly. So multi-fidelity, I'll skip this, but the idea is once you can place sensors, you have access to Mother Nature, and Mother Nature can give you the right solutions. So now you have a situation where you have some data which is very high quality, it's the sensor data, and then you have a lot of data which is computational data, which is not quite as accurate. And the question is, can you combine the two so that you can get much better predictions than with the computational model itself by using the little data you have from the sensors? And because you have placed the sensors carefully, this can be hugely beneficial. But I won't talk about that just in the interest of time. Okay, so just to finish on time here. So the point I'm making is that in order to do digital twins, and in order to use artificial intelligence to build and drive digital twins, we have to be able to build reduced order models of complex assets. Now, everything I have talked about is single physics problems. Multi-physics problems is more complicated. It's an area of research. But then once we have that, we can begin to combine these methods with data-driven technology, and this is where the opportunity is. The fusion of these with the data multi-fidelity, assimilation, and also this is what enables you to build tools that allows you to make decisions. And the fourth bullet is an important one, which says that the small data problem, which is the one we've talked about, is not going to be solved by the computer scientists. Okay, the computer scientists are pushing forward with their neural nets and what have you, and all their cat pictures. But this is not a cat picture problem. Okay, this is a problem that would only be solved if we combine modeling with data science. So this is an extremely rich area. There's a lot of things to do. I have only scratched the surface. It's interdisciplinary, it's challenging. But if you can get it to work, it can have a huge impact in the next industrial revolution. Here are some papers for those of you who are interested in that. Everything I've shown is just a few years old. So there's, and it's really just the beginning of things. So with that, thank you very much for your attention.
Thank you. That was really great. A really nice talk. Thank you. I see we have one question. I'll just read it out loud. Is the research work based on in-house software where all the high quality discretization and solvers are incorporated, or is it partly based on commercial software? And is it all in Python?
Honestly, I don't care which language it's in. Okay, for all I care, you can write your own language. That's completely uninteresting to me which language is written in. So it's a mix of things. I mean, most of the software is actually open source software that we have not developed, but we simply take and use. The example I showed with the nonlinear case. So now it becomes what is called non-intrusive, which means I don't need to know the solver. I just need to say, if I give you the parameter, I give you the materials, whatever, you give me a solution. That's all I need. How you get it, I don't care about that. Okay, so this can be a commercial solver, it can be an in-house, it can be a classified solver, it can be anything you want. Now, the case where we go to these very complicated, like the oil rig, that's actually a piece of software that is developed by a company at EPFL. I'm not part of it, but I work with them. The technology is published in the open literature, but you know, coding it up is a bit of a nightmare. But the key point is this: you don't have to have access to the inside of the code. You can do non-intrusive reduced order models at this point in time, and once you have that with the Gaussian process or whatever, you can do everything that I showed you. So it can be written in algol, and you can still do it.
Cool. There's one more question that from the chat. So the question is, what if hardware or solvers becomes 1,000 times faster? I assume it means that we then need to reduce other models if we can just solve it fast on using conventional methods. If I misunderstood, then please tell me in the chat.
No, but this is a legitimate question. All that would happen is I'll be interested in a problem which is 1,000 times bigger. This problem will not go away. Okay, I understand completely the sentiment. It's saying, oh, but you know, the hardware is getting faster and faster. So you know, who cares? We can just do it in a straightforward way. And the answer is no. I mean, let's say we're looking at the oil with the jacket here, which is the most complicated case. Compared to an aircraft, where you have the electric system and the engines and the navigation system and the antennas and the structure and everything, you want to do the whole thing. You know, this is many orders of magnitude beyond what we can do. So it's completely unimportant how much faster the hardware is, unless you get to, okay, I can give you 10 millions, many orders of magnitude acceleration. Well, then maybe, but I think certainly in my lifetime, waiting for the hardware to get faster will not solve the problem.
Okay, cool. Let's take one last question. I reformulate the question a little bit. So it's about physics-informed neural networks, asking whether they are better than reduced order models. But let me rephrase it, saying that what's your view or experience with physics-informed neural networks? Now that you briefly mentioned neural networks, but not really touching the subject a lot.
Yeah.
So can you give some brief comments on that?
Yeah. So the challenge is, we have actually worked with on physics-informed neural networks. I just didn't talk about it, but so the challenge with neural network technology in general for physical problems is it's very hard to get good accuracy. So if 10% error, or maybe even 1% error, you work hard at it, it's good enough for what you do, then some of these techniques are very interesting. But for if you will, for real problems, for more complicated problems, training the network is actually very difficult. So what is happening is that you're pushing the sort of the blame into the neural net, into the training. So I think that the things to keep in mind is, what kind of accuracy do you want? If 10% accuracy, or maybe even 1% accuracy, is all you care about, well, then it could be that physics-informed neural network is something for you to work on. If you want more accuracy than that, it'll be very difficult to do that with a neural net, because of training. And then there's the other aspect of it, which is you basically have no guarantees, no understanding, and no insight into the accuracy of the neural net output. Okay, so you can train, you can do, but the understanding of what the neural net does for you theoretically is very, very limited. So the approach that we have taken is actually to use neural nets, also physics-informed neural nets, in combination with reduced order models, so that you have everything that you do with reduced order models, with the basis and all of this, but then you build a neural net that predicts the coefficients using physics-informed neural networks. And that actually turns out to work quite well, but still it is difficult to get, let's say, more than 3 digits accuracy. If you do physics-informed neural networks directly on the solution, you get very, very large networks, because you have to predict all the degrees of freedom, then you do convolutional nets and all these sorts of things. But we've taken the approach of doing all these sorts of things, but in combination with the reduced order model, to reduce the dimensionality of the problem. And that seems to work quite well, but it has its limitations.
Perfect. And then one quick last question to elaborate on that. So how do you see the future of neural networks? Do you see that we can surpass the theoretical boundaries such that we can understand and use neural networks in to get the same kind of results and interpretability as we get from the other methods, or is it a lost cause?
Oh, I don't know if it's a lost cause, but it's one of those things that it can be solved tomorrow or 100 years from now. I mean, the understanding of these nonlinear approximations, which it's a nonlinear map between input output, that you, for the simplest ones, for the very complicated ones, the convolution nets and so on, is very complicated. Understanding what that nonlinear map does and how you deal with it is one thing, but then the other thing is, because you can prove that a neural net with a reasonable activation function and so on can approximate any function spectrally accurately. Okay, which means you can get extremely high accuracy from the neural net. It's just that it is effectively impossible to find an initial condition when you train that gives you that solution. So therefore you find there's a very large number of local minima where you get, typically 10 to the minus 2 type accuracy. Maybe 10 to the minus 3 is really difficult if you're careful with the parameterization. So the theoretical understanding will come sooner or later, but the practical issues of actually training the networks requires really a massive leap forward in how we solve highly nonlinear, non-convex optimization problems. And this is, this is just, it's a global optimization. I mean, this is the holy grail of optimization. So will we ever get there? Yeah, we probably will get there eventually. But even if we do, I'm still not a big fan of this notion that we should forget about our physics models and just do neural nets. We've spent 75 years on solving PDEs. We're actually pretty good at it. I don't see any reason, I have seen no reason why we should throw this away. But the combination of the two, that's also what I'm advocating here, the combination of the two, that can potentially be very powerful.
Perfect. Thank you very much. Unfortunately, I don't think we have more time for questions now. I think we have to
sorry for taking more time, but
no, it's fine. We did start a little bit later, and it was interesting stuff. So at least